Alright, let's talk today about electron configurations and periodic trends. Last week we talked about orbital configurations, and those we were able to get by looking at Aufbau principle. So this was this whole loop-de-loop-de-loop thing that we discussed. So the idea is that electrons get put into orbitals and therefore subshells based on the energy that's required in order to enter them. And so that's why you enter 1s, then 2s, then 2p, etc., and why 4s is entered before 3d. And so this was Aufbau's principle that allowed us to fill in these orbitals based on the number of electrons. So the first thing we had to do is decide, how many total electrons does an element have? So for instance, we looked at nitrogen. Nitrogen has 7 electrons. So we would have gone ahead and draw. Let me grab my pen over here. We would have drawn in 1, 2, 3, 4, 5, 6, 7 electrons for neon, and this would have been the orbital configuration. Alright, so then the question is, well, what's this electron configuration thing we're talking about? Basically, all it is you take the number of electrons within any subshell and you write it as a superscript above the letter. So since there were 2 electrons in this subshell, we drew a 2 over the 1s. And 2s, there are 2 electrons, so that gets a superscript of 2. In this 2p, there are 3 electrons that we count, so it gets a superscript of 3. So if we were to write out the electron configuration, then electron configuration doesn't have the boxes, it doesn't have the lines that shows the arrows. That's all orbital configuration. Electron configuration simply is those items that you see here. The 1s, the 2s, the 1s2, 2s2, 2p3. So electron configuration is simply a shorthand way of denoting where electrons reside inside the subshells. Alright, so that's why we've got here for silicon. Silicon's got 1s2, 2s2, 6 in your 2p, 2 in the 3s, and then 2 in 3p. And so that's why it gets this electron configuration shown here. Now notice, it's got core electrons denoted and valence electrons denoted. Now valence electrons, remember, were those in the outer shell. So if you're asked the question, what is the outer energy level for silicon? That would be 3, just because n of 3 is the furthest out. So in order to figure out how many valence electrons it has, we look and we just count. There are 2 valence electrons in the s subshell, and there are 2 electrons in the p subshell. So that gives a total of 4 valence electrons. And if we look at our periodic table, we would have known that silicon, oh yes it does, it's right below carbon, and it's in group 4, and so since it's in that group 4, then we know that it's got 4 valence electrons. Alright, so here's a whole bunch of different examples the book gave us. Note the electron configuration is here, and if you count all the superscripts up, they're all denoted by the number of electrons total in the atom. Okay? Notice each time you just get 1 more electron, and it just comes back and it refills the orbital each time anew. So these are just all examples of what's going on between electron configurations to orbital diagrams. It's definitely helpful to fill the orbital diagram first, and then the electron configuration next. So, for instance, let's look at another example that goes a little higher energy level. So selenium. So with selenium, what we've got here is all these orbitals are filled. So you would think, oh, this would be the proper way to write it, right? Because the 3p goes before the 4s goes before 3d before 4p10, or 4p4. But this is for orbital diagrams. That's the order you list things for orbitals. Orbitals go by energy. Whenever you want to list the electron configuration, you want to always keep it so your valence electrons, these denoted in yellow, make sure that they're written last. Okay? So what that means is it's better to be written like this, where your 4s2 and your 4p4 go last. Because then you've got your 6 valence electrons can be counted, where you've got your 2 and your 4, just a glance. You can just glance at it and tell that you have 6 electrons, because you write these 4s first. So notice it goes all the 1s, all the 2s, all the 3s, and then all the 4s. And because n equals 4 is your highest energy level, that's where your valence electrons are residing. So if you asked how many valence electrons does selenium have, you'd say 6. And if you look once again at your periodic table, selenium is under sulfur, which is under oxygen, which is in your family of 6. Therefore, it has 6 electrons in the valence shell. Alright, so let's look at some of this electron configuration shorthand. So the main difference between configuration shorthand and just the configurations is it's a lot shorter to write. And so everybody got tired of writing, oh, well, I know 1s is always filled, I know 2s is filled. So what they did was they came up with a shorthand method to help us figure out how to relate each element to each other. Okay, so for instance, notice carbon has the same configuration as nitrogen, except for nitrogen has one more electron, and so on and so forth. Okay, notice everything in group 1A now, it all ends in S1. Everything in 2A ends in S2, 2s2, 2p1, 2s2, 2p2, etc. So if it's in the same family, remember families share characteristics, they're going to have the same kind of structure there at the end. So the idea here is everything ends in S2, 2p1, okay? But note, as you go down, it's almost as if everything here starts with a 1, a 2, and a 3, okay? 1s1, 2s1, 2s2. So if I were to say, oh, okay, sulfur, what's underneath sulfur? And you look at the periodic table and you say it's selenium. Okay, the one we just did. Based on this, it's in our row 4, so you would assume it is 4, because notice it went 2, 3, so it would be 4s, same number of s, 2, and then 4p, 4, just based on its position on the periodic table. Okay, so note, you can kind of denote and figure out the shorthand just based on its position. Or for instance, what if we were to look at what's underneath silicon? That is Ge. Okay, germanium. So germanium should have 4s2, 4p2, if you can read my lovely mouse handwriting. Alright, so that's what's going on here. But the question is, well, how does this save you any time? Alright, so if you look at oxygen, oxygen is simply nitrogen plus 1 electron. Or it is beryllium plus 1, 2, 3, 4 electrons. Or it's helium plus 1, 2, 3, 4, 5, 6 electrons. So what that means is we can compare oxygen to everything that comes before it. Okay? And in particular, you're interested in its comparison to helium. And we'll talk about why that is here in a second. Okay? So here's kind of a summary of everything. Okay? So we before were just looking at this one, the 1 and the 3 groups. Okay, so notice there were no D's at that point. D's belong to transition metals. Okay? And then the same thing for F. You don't have F's that are non-transition metals, or you've really got them down here in these bottom group. Okay? So what that means is everything here, if I just randomly pick a point, say here, alright, I know it's got 2 of the S2s, okay, so it's got 2s1, 2s2, and I know it also has 2p1, 2p2, 2p3, and 2p4, okay, and that's because this is your P area in pink, this is your D, and this is your S, and you literally can just count 4s1, 4s2, 7s1, 7s2, okay? Or to come over here, 5p1, 5p2, 5p3, 5p4, 5p5, 5p6, okay? So this last one here would therefore have 5p6, okay? So basically the number and its location tells you the outer configuration of the element. Alright? The other thing to note, phosphorus. It's got the same configuration as neon. So how we write that is we write neon in brackets. Then, what does phosphorus have after neon? It has an electron here and 3s1 and 3s2. So it's got 3s2. What else does it have? It also has 3 electrons, 1, 2, 3 here. So it'd be neon 3s2, 3p3. Okay, and that's just kind of shorthand. Same thing for D. Okay, so anything D, you know, it starts 1, 2, 3, 4, all the way up to 10, because you can fit 10 electrons in a d orbital. And F, can you guess how many elements are here? 14, because F has 14 electrons. So you can do that the exact same way, except for this one starts with 3D. Okay, same thing here. This would be 4D, 5D, and 6D. Okay, and as far as these two elements here, so you got your La here, it should have 4F is where you're starting. 5F is where you're starting. Okay, and that's basically because 4F comes after 5D. Okay, 5F comes after 6D. If you look back at Aufbau's principle, the whole diagrammy thing that we were looking at. Alright, so this is just kind of getting at how you can just look at the periodic table. Even if you don't do all the orbitals, you can figure out what the electron configuration is. And then you can write a shorthand method. So when I say shorthand, this is what I mean, and we'll look at a couple examples as well. But this is a really good way to double check yourself and make sure you're doing it all properly. Alright, so just another example. Arsenic. It has the same electron configuration as argon. Okay, so you can write argon. Then what's after argon? 4s1, 4s2. So 4s2. How many are in 3D? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So then we have 3D, 10. And then after that we got 4p1, 4p2, 4p3. So 4p3. Alright, and that would be the shorthand configuration. With one exception. Whenever you've got electron configurations, remember how are we supposed to order it? Can we order it according to energy levels? No, you have to group all of the 3's first and all of the 4's last. That way you can tell how many valence electrons you have. So it would be argon 3d10, 4s2, 4p3. Alright, so this would be correct. That way these last two denote your valence electrons. So you can look really quick and say 2 electrons plus 3 electrons, 5 valence electrons. And what do you know? We're in group 5A, and we have 5 valence electrons. Alright, so once again, kind of looking at all of these trends that we noticed earlier, everything here ends with S1, everything here ends with S2. So note, that's why we're getting these ions. Is sodium has 3s1, so it's got 1 electron all by itself in the S shell. So it makes a lot of sense for it to get rid of that 1 electron and take on the same configuration as neon. Alright, so that's why sodium's positive. It's positive because neon is really stable, so it wants to lose that 1 single electron and become neon. Okay, so basically, the way to tell this is the electron, like bromine or calcium or any of these, they're going to take on the electron configuration of the nearest noble metal. Okay, so think about it this way. Bromine, which one's is nearest? That would be krypton. So it's going to add an electron, so instead of having 4p5, it'll now have 4p6. And that's why you end up with bromine minus. Okay? Or calcium. The nearest one to calcium is argon, number 18. In order to get there, calcium has to lose 2 electrons and take on the configuration 3s2, 3p6. Alright, so that's another reason as to why we've got these ion charges. And if you look at everything you guys have already known about them, it proves to be true. That's why sodium's always +1, magnesium 2+, etc. And so basically you can find their electron configuration just like any other electron or any other atom. You just first have to ask the question, how many electrons are total inside the molecule, the atom, excuse me. So for instance, nitrogen, it's got 7 electrons normally, added 3 electrons, so now it's got 10 electrons. And if you look, neon has an atomic number of 10. so they have the same electron configuration. So it's called isoelectronic. All right. So just kind of noting that this is why electrons form the species that they do. They're trying to become more stable. They're trying to be like those snooty noble gases. Okay. All right. So there are exceptions to every rule. All right. And with the periodic table, no different. All right. So just as we talked about before, about how the blue is your S block elements, D, P, and then F. And so basically, whenever we're coming along here, we want to say, all right, what should it be? What is it really? So for instance, 4s1, 4s2, then we start to fill 3d. So we've got 3d1, then we fill 3d2, 3d3, 3d4. Wait, why is chromium 3d5? I thought it was supposed to be 4s2, 3d4. So that's definitely an exception, all right? Because if you think about it this way, 4s1, what? I thought I was supposed to fill through 4s2 all the way before filling 3d. While that's true, think of it like this. Here is your 4s shell, and then here is your 3d shell. All right? So if you have your 2 electrons here in your 4s shell already, so just like vanadium, then you've got 4 electrons here, or really 3, okay, because it had 4s2, 3d2, so this is vanadium. That next electron wants to go here, all right? But what's important is you have this electron right here, it sees the open room, and it says, hey, I want to go take it over. So it shifts over here, okay? It's the same thing as if you notice that you're sharing a room in the dorm with some crazy guy, right? And then every room in the rest of your hallway only has one person to a dorm. And now an end room opened up on the end. And you're like, why do I have to be the only one with a roommate? So you go bail, ship, switch on over here and fill that last orbital. So that's why, is basically this one electron from the 4s1 is stolen and fills that 3d5. Basically, it takes a lot less energy to have all of your electrons with one, all of your orbitals with one, than to have 2 and 1. And that's only really the case for your D block elements and your F block elements. And so you'll notice that there are a lot of exceptions to this. So everything highlighted here in red is an exception. I do think it's a really good just kind of practice to go through and be like, why is this an exception? Why is this an exception, etc. Just kind of generally, if we look at these two here, 4s is supposed to fill before 3d, 5s is supposed to fill before 4d, but yet that's not the case. So you guys are going to be accountable for these two periods, periods 4 and 5. These guys are just extra, okay? So if you're kind of thinking, okay, what's 5d supposed to fill, then f, 6d1 supposed to fill, then then f, but yet this doesn't have any f. So that's kind of what you're thinking about, is what makes them an exception to the general rule. Alright, so now we're kind of changing gears. We're going to be talking, I'm going to do another little video where I'm just going to record how to draw out the shorthand and how to do the electron configurations and electron orbitals, but that'll be in a separate slide to help you with homework. Now I want to talk about periodic trends. Alright, so it's kind of changing gears. So we've got electron configurations we've figured out, and we've also figured out electron orbital configurations. So now what we've got is periodic trends. The idea here is that you can learn so much just by looking at the periodic table. Even just checking your orbital diagrams or checking your electron configurations by looking at the periodic table. So periodic trends, let's see what we got. Alright, so first off, atomic size. If you notice, the smallest atoms are those in the top right hand corner and the bottom left are the biggest. If you think about it, that makes a lot of sense because atomic size is the distance between the outermost electron and the nucleus. So the more and more electrons you get, the greater number and the greater the size. Because if you think about it, n equals 1 all the way down to n equals 6, n equals 6 has more energy, and the thing that varied between n equals 1 and n equals 6 is the size. And so that's why all these spheres are just getting bigger and bigger and bigger. And so that's why cesium is so much bigger than hydrogen, is because it has a lot more electron orbitals with higher energy levels and it's getting bigger. All right, but then the question is, okay, well, if they all have n equals 6, why are these not all the same size? All right, so that's where this but down here comes in. As you increase the number of protons in your nucleus, you pull the electrons in closer to the nucleus. So the thing here is, between cesium and barium, they both have a 6s orbital. All right, that 6s orbital is, here you've got 1 electron in it, here you've got 2. Barium is just slightly bigger. You added 1 more proton, and so the extra proton pulls in those outer electrons just a little bit closer, making it smaller. All right, so that's why it decreases across this way. If we were to summarize it, I would summarize it in this way. And I've printed all these slides kind of on one little handout that I'll put on D2L for you if it helps you study. So basically there's 3 different periodic trends we're going to look at, and one of them is atomic size. The idea is they're bigger toward the bottom left, smaller toward the top right. Alright, so let's do some practice. So remember, bigger bottom left. So which atom has the larger atomic size, carbon or oxygen? Feel free to pause it right now, think about it for a second, and then come up with an answer. I hope you came up with carbon. Carbon's closer to the bottom left, so it should be larger. Okay, what about lithium and potassium? Potassium's closer to the bottom left, it's larger. Aluminum and carbon. Aluminum's closer to the bottom left, it's larger. What about these two? They're tricky, huh? They're both about equal distance from the bottom left. So really when they get like equal distance, you really have to do experiments to figure out which one is larger. So I'm not going to be asking you on the exam or anything like this, but they're just kind of interesting to think about and kind of consider. Okay, the next trend is ionization energy, and that's the energy required to remove an electron from an atom in the gaseous state. So you guys already kind of know about this, even though you didn't know its name. Alright, so for instance, if you look at all of the group 1 elements, they normally form a +1. So we're talking about all of these guys over here. They form a +1 because they lose an electron. So the idea here is these guys want to give away electrons really, really easily. Okay? So they have a low ionization energy because it doesn't take a lot of energy to remove an electron. They're giving it away free like the 10-cent box at a garage sale. Okay, so they're just super ready to get rid of those electrons. As you come over here to this side, they all want to form negative compounds, which means they really want to steal electrons. So if you're trying to steal from them, that makes them really unhappy, and it's really hard to remove an electron. So if fluorine has 7 electrons, it wants to have 8. So it's going to do all the stealing. But if you were to try and remove one from it to make it be F+, that would take so much energy. And so the idea here is that it requires little energy to remove electrons in this bottom left-hand corner. And as you get to the top right, they're going to hang on to their electrons more, and that energy required to remove an electron is going to be huge. So to kind of summarize it a little bit more here, that as you increase the principal quantum number, you're also increasing the distance, okay, that negatively charged electron is from the positive nucleus. So it takes less energy to separate them from each other. Alright, so kind of the idea here is as that number gets bigger, going down it's going to take less energy to separate it. So that's why it's smallest in the bottom left as opposed to the top right. And so you guys were able to tell intuitively why left to right it gets harder, but as it goes to the bottom, that's due to, once again, you're adding more protons, more neutrons, and you're getting closer to the higher quantum numbers. Alright, so summarize that. The main thing is, if it's big ionization energy, top right, small ionization energy, bottom left. Okay, so magnesium or phosphorus, which one has a larger ionization energy? Phosphorus is closer to the top right, so that one has our higher ionization energy. Arsenic, or can't remember what SB stands for. Let's go with antimony, that's right. So antimony or arsenic, which one's larger? Arsenic, because it's closer to the top right. Nitrogen or silicon? Nitrogen, because it's closer to the top right. Okay, oxygen or chlorine? This is another one of those tricky ones that's determined experimentally. Okay, because they're about equal distance from that top right. Alright, so Metallic character. You guys already know these are all your nonmetals, these are all your metals. So basically, the only main thing to notice here is that your metals, it gets more metallic as it gets to the bottom left, it gets less metallic toward the top right. Alright, so metallic bottom left, nonmetals top right. Kind of the idea is it's really related to ionization energy. The idea is your metals are the ones that form cations, your nonmetals form anions. So, selenium or tellurium, which one has a larger metallic character? You've got SN. Excuse me, what did I call it earlier? Who knows? This is tin. So, tin is larger metallic character. Once again, tin has a larger metallic character. It's closest to the bottom left. Tellurium or bromine. Te, that's right. Te has the larger metallic character. Okay? And this is another case where it's really hard to tell without experimental data to back yourself up. Okay, so this is kind of the summary slide I was telling you about. I put it up on D2L, that way you can print it and look at it. So, atomic size, metallic character, ionization energy. Alright, I feel like it's been a long talk here. I feel like I've been talking forever, and you probably agree. So, here's just kind of a summary of everything we've learned from Chapter 9. Energy, wavelength, and frequency, all related to each other and to color. You're able to tell the difference between emission, absorption, and reflection. N is your principal quantum number, and it's also the energy level. S is your subshell that has one orbital in it. It's spherical. P is your subshell that has 3 orbitals in it, and they're all dumbbells. D is your subshell with 5 orbitals, and you've got 4 clovers and 1 dumbbell with a ring around it. And then F has 7 orbitals. Every orbital can hold a max of 2 electrons. Aufbau principle identifies the energy required for each subshell and for N, so that's the stair-step thing with the red lines through it. Okay, and then lastly, you guys know the difference between an orbital diagram. So if I ever ask for an orbital diagram and you give me this, it's wrong. If I ask for an electron configuration and you give me this, it's wrong. Know the difference between them. Each orbital does have a certain shape. Know what the shapes are. Know that there are exceptions, especially in the transition metals. And then note that ions have electron configurations too. Okay, so really in reality, you've got all this information to learn, all the stuff on the previous 2 slides. So you got your summary slide and these 2 review slides. I hope this is helpful to you, and check out the next video where I'm just going to go through the